In this podcast, I'll be reviewing 3 laws of logarithms that we can use to either rewrite expressions or to solve equations. So first of all, a couple parameters on these logarithms. The base that we're going to be using, which is little a, is going to be a positive number that's not equal to 1. For example, we could have a log base 7 or a log base 2. We could have a fraction, log base 1/3, but it won't be a negative number and it won't be 1. Okay, now big A, B, and C are also going to be real numbers. A and B are both going to be positive. C could be a negative, and I can show you an example of that. But A and B, it might be an example where we want log base 7 of 7. Okay, so our goal when we're using a logarithm is to find the exponent that takes the base to what we're taking the log of. So log base 7 of 7 is 1 because 7 to the first power equals 7. And usually when I start teaching logarithms, one of the first things that I do, oops, I wrote that wrong. One of the first things that I do is I show students how to rewrite them. So log base 7 of 7 equals 1 because 7 to the first power equals 7. There's my base, there's my exponent, that's what we're taking the log of. So log base 7 of 49 would equal 2 because 7 squared equals 49. Okay, so getting back to the laws of logarithms. In the first one, it shows us that log base A of the product AB equals the sum of log base A of A plus log base A of B. Notice that little a and big A are little a is a different number from big A, just because one is lowercase and the other one's uppercase. Okay, what I like to do is I like to give an example of, let's say we've got log base 2 of 8 and log base 2 of 4. If you're adding these two logarithms together, it would actually be the same thing as finding the log base 2 of 8 times 4, which is equal to log base 2 of 32. Now let's think about this. Log base 2 of 8. 2 to what power makes 8? And that would be 3. And log base 2 of 4. 2 to what power makes 4? That would be 2. If I add those two logarithms together, I get 5. Is that going to be the exponent that would take 2 to 32? Yeah, 2 to the 5th equals 32. So the formula worked, the law worked, and a lot of it has to do, and I usually show this to my students in class, I go back to the rules of exponents that we learned in Algebra 1. 2 cubed times 2 squared equals 2 to the 5th. If you're multiplying powers with the same base, you add the exponents. Logarithms are basically exponents. So if you're adding logarithms, it's like adding the exponents in a multiplication problem. Now, number 2, this one shows us that if we're subtracting two logarithms with the same base, we can divide out what we're taking the logs of. All right, and this also goes along with what we learned in Algebra 1, that if you have, let's say you have x to the 8th divided by x cubed, we can subtract the exponents to get x to the 5th. So if we're subtracting two exponents, that's the same as, that comes from a problem where we were dividing. Okay, and we'll see examples of that. And then the third one says, if you have the logarithm of a multiple of something, or excuse me, if you have the logarithm of something that's taken to a power, you can pull that power to the front of the problem, and it becomes the multiple of a logarithm. Okay, again, this kind of goes along with, let's say you've got 3 squared and you take that to the 4th power. Well, we're going to multiply those exponents together to get 3 to the 8th. Okay, and right here, this logarithm is an exponent, and then we're multiplying it by the other one. An example that I like to give students of this one in class would be, let's say we have log base 7 of 7 squared. Well, that's the same thing as saying log base 7 of 49, which equals 2. If I pull that 2 to the front, I get 2 times log base 7 of 7, and log base 7 of 7 is 1, so this just makes 2 times 1, which is 2. So either way you do it, it's okay. Now, we use these properties when it helps us rewrite an expression or solve an equation. So here's a couple of examples. In the first one, if you were trying to find log base 2 of 80, it would not be a nice rational answer. Neither would log base 2 of 5. But if I use the property that subtracting two logs with the same base, I would get 80 divided by 5. That's what I'm taking the log of. And you remember that 80 divided by 5 is 16. Now all you have to do is think 2 to what power makes 16? And that answer is 4. So by combining it into one logarithm problem, it made the problem easier for us. Same for the second one. If I'm trying to find log base 6 of 4, I have to think 6 to what power makes 4? It's not going to be a nice answer. But if I add these two logarithms together and I combine them by multiplying 4 and 9 to make 36, then I just have to think 6 to what power equals 36? And of course that answer is 2. In the third one, I don't want to take 25 and cube it because that's going to make a really big number. I'm going to move the 3 in front and have 3 times log base 5 of 25. And then I'm going to evaluate the logarithm because 5 squared is 25. So log base 5 of 25 is 2, which gives me an answer of 6. Now, the last one is an expression, and it's a 3-term expression. If I'm going to combine these together into one logarithm, the first thing I would do is actually put the numbers in front back into the problem. So I'm going to end up with log base 8 of x minus log base 8 of y cubed plus log base 8 of z to the 4th. Now, from left to right, if I'm subtracting two logarithms, I can combine it into log base 8 of x divided by y cubed, and then I'm adding the logarithm log base 8 of z to the 4th, which means I can multiply it. Now, that z to the 4th is going to go to the top of that expression, so my final answer will be log base 8 of x z to the 4th divided by y cubed. I ended up with one logarithm, which would be considered a simplified expression in some cases. Okay, now, the next example, I'd like to go the opposite way, which is to use the laws of logarithms to expand each expression. You might do something like this in calculus. Okay, so in the first one, I would, because these are being multiplied, I would use that first rule that a logarithm that's being multiplied, you can expand into two logarithms that are being added. Okay, so make sure you keep the same base, and we're going to add log base 2 of 8 to log base 2 of x. Now, in this case, because log base 2 of 8 is a nice answer, I'm just going to change that to 3. Okay. In the second one, I've got a couple things going on here. One of the things that I would do first is get rid of that cube root. So I'm going to take the natural log of the product of AB divided by c to the 1/3 power. Okay, now I'm going to expand this into the natural log of A plus the natural log of B minus the natural log of c to the 1/3. I'm subtracting the c to the 1/3 because it's being divided in the original problem. And then one other thing I could do is move that 1/3 power to the front of the natural log of c. All right, last problem. We're going to use the laws of logarithms to solve an equation. Now, we want to try to figure out what value of x makes this equation true. And you can't just combine the x's together. What we want to do is combine the two logarithms by using the rule that adding two logarithms is the same as one logarithm where we have the product of x plus 2x minus 1. Now, the base of this problem, even though you don't see it, is 10. So the next thing I'm going to do, and this usually confuses students, they don't always see this, is I'm going to rewrite this without the logarithm. I have x plus 2 times the quantity x minus 1, which I'm going to FOIL out. X squared plus x minus 2 equals 10 to the first power. Okay, then this is a quadratic, so I'm going to subtract 10, set it equal to 0, x squared plus x minus 12 equals 0, and then I'm going to try to factor this one. I have to think, what multiplies to make negative 12 that adds to be 1? I'm going to go with plus 4 minus 3. Okay, which means the solutions are negative 4 and positive 3. Now be careful. If we go back to the original problem, if you put a 3 in here, you're going to get the log of 5 plus the log of 2. If you added those two logarithms together, that would be the same as the log of 5 times 2, which is 10. And the base of 10 shows you that 10 to the first power does in fact make 10. So that one worked. But if you put negative 4 up in this original problem, the problem with this is that it's going to give you the log of a negative number. The log of negative 2 plus the log of negative 5. And unfortunately, you cannot take the logarithm of a negative. So we at this point would say that this is an extraneous solution or a false solution. The only good answer in this case is the 3. And there's your 3 laws of logarithms. Thank you.